I hope everyone has given the first tutorial, first assignment for the this course. Is it? You can unmute yourself and let me know. Have you? Can you hear me?
Yes, sir.
Okay. So have you completed your first assignment?
Yes, sir.
Okay. So I think yeah, we can start the session. So yeah. So coming on to the performance. Of the Today we'll be dealing with the performance parameters which are used to quantify an aircraft, uh, and some of the parameters will be dealing with the air breathing engine. We'll be dealing with the air breathing engine, uh, then how we can quantify their efficiencies, the propulsion efficiency, thermal efficiency, propeller efficiency in case of a turboprop and a turbo shaft engine, then the overall efficiency. We'll be dealing with in a very briefly how a rocket engine can be can be parameterized using the static thrust, static performance such as specific impulse and thrust. So let us start with the efficiencies first for our air breathing engine. So So a propulsion efficiency basically represents how much the part of the kinetic energy that is being imparted to the exhaust gases is being transferred into thrust. So so the thrust equation for any type of aircraft is given as this, where ma is the mass of the gas, mass of the air which is coming into the engine. So consider this is there is a you have a aircraft, there is a compressor or a fan, compressor, then it is being driven by the turbine, and you have a combustion chamber. So basically this m dot a represents the mass of air that is coming into the engine. This the second term represents the exhaust velocity from the gas. Higher the exhaust velocity, higher will be the thrust. Similarly, VA is the velocity at which the air is coming into the engine. Whereas P exit and PA. P exit represent the static pressure at the exit of the engine. So this is not necessary. There is no compulsion that the exit pressure will always be equal to atmospheric pressure. So this thing will be studied in the later part of the course. But for a time being, let us consider that this equation gives you the thrust of the aircraft. So yeah, and A exit is the area at the exit of the engine. Now the propulsion efficiency is the thrust power, which is this quantity represents the power, which is this force multiplied by the velocity of the aircraft. U is the velocity of the aircraft. So these two quantities represents the propulsion power, and at the bottom it represents the bottom part, denominator part represents the kinetic energy of the exhaust, and this term represents the kinetic energy of the inlet. So what amount of kinetic energy change is being transferred to the vehicle? This represents your propulsion efficiency. So yeah, so let us see how this propulsion efficiency varies uh, with the flight velocity. Uh, Here in the x-axis represent the flight speed by the exhaust velocity. At this point, the flight speed is equal to uh, the flight exhaust velocity. At this point, the flight velocity is zero. The flight velocity is zero. So this represents the uh, static state. Yeah, as you can see, if you increase the velocity, uh, if the velocity of the aircraft is higher, um, which is equal to the exhaust velocity, then the propulsion efficiency is maximum. But it should also be taken care that the thrust, this represents the thrust, that as the flight velocity increases, the thrust also decreases. So yeah, and this can be theoretically. Let us see how this propulsion efficiency is given as. So this is two from this equation. From this equation, these two equations, we have propulsion efficiency is equal to uh, m dot a into uh, v exhaust minus va into va. So yeah, and at the bottom we have, I'm assuming that PAE is equal to PA, which is the exhaust is coming out at a design condition. So when this will be clear when we'll be dealing with the gas dynamic expect of the um, flow. So this is because of the gas dynamics uh, uh, consideration. Now let us see this equation. So this is UE minus UE square by 2. So if you solve this, you will get 2 VA by VE plus VA. Then you will get 2 times of VA by VXZ by 1 plus VA by VXZ. So yeah, so 1 plus U by UXZ. Let's consider this quantity as X. So you get 2X, 1 plus X, d eta P. Okay, yeah, so this is one. So this is, yeah. So you have eta P as this, the eta P by dx is equal to minus 2x 1 plus x square, and yeah, and you have plus 2 1 plus x, so you get 1 minus x by 1 plus x square. So x is equal to 1, which means UE by U is equal to 1, which represents the maximum efficiency occurs when UE is equal to U exhaust. So this represents this is why your proportional efficiency is maximum at this point. Yeah. So yeah, let us solve one problem. Let us see how whether we can answer this thing. So you have to comment on the propulsion efficiency and the inlet area of the engine, uh, and you have to compare two aircrafts. One is a fighter jet and one is the commercial aircraft. So I'll give you 2 minutes to think about this question and to answer this. Whether here AF represents the inlet area of the aircraft. A represents the inlet area of the aircraft, and F is represents the fighter jet, and C represents your commercial jet. So you have to answer which one will be which of the following is correct? And eta P represents the propulsion efficiency. Okay, so this is should be F. Eta represents the propulsion efficiency. So yeah. So I'll give you 2 minutes to think, and you can answer that after that. Yeah. What do you think? Like the propulsion efficiency. Let us comment on this first. Whether the propulsion efficiency for a fighter jet will be higher, or a propulsion efficiency for a commercial jet will be higher. So anyone, if you wants to answer this,
Sorry, fighter jet.
fighter jet, fighter jet will be higher. Propulsion efficiency for a fighter jet will be higher. Is it?
Yes, sir.
Yes, sir.
Okay. Okay. So how about the area, inlet area?
Sir, less.
Less. Okay. So you're saying propulsion efficiency for a aircraft, fighter aircraft will be higher and the area will be less. Is it?
Yes, sir.
And why do you say so?
Sir, if the area is lesser than the speed of the fighter jet would be the increasing, so that it increases kinetic energy, proper efficiency would increase.
Okay. So no, I don't think this is a correct explanation for this. Uh, I'll give you a minute to think once. Then you can answer that. So, okay. So, anybody else wants to answer this question? Uh, okay, maybe I'll repeat the question. For a fight, you have to compare the inlet area for a fighter jet and a commercial aircrafts. Which one will be higher or lower, and also the propulsion efficiency. Anybody?
Sir, in case of fighter jets, if the area is least, sir, then it can pass the over of wind opposition flow, sir. In case of commercial flights, the area would be comparatively higher than the fighter jet, so that it won't be moving in that speed comparatively to jet fighter.
So basically, you're saying for a fighter jet, as it cruises at a faster speed, it needs a smaller area to take in for the same amount of air, is it?
Yes, sir.
It is correct, man. Yeah, yeah. So okay. So coming on to the answer for this, so as UE by U exit for a fighter jet, U exit is by U is comparable to yeah, they are comparable. So the thrust, okay, one minute. Yeah. So okay, propulsion efficiency for yeah, it goes as if the difference between the U by UE is more, therefore yeah, so the propulsion efficiency will be less as given in this plot. As the difference between U by UE is less, is more, the propulsion efficiency will be less from this curve. So, for a fighter jet, the U by UE is comparable. So, it's not comparable. Sorry. So the exhaust velocity, the at the fighter jets, the exhaust comes out at a Mach nearly about Mach number 2, and they cruise around Mach number 1.5, whereas the fighter jet, the commercial jet, they cruise around Mach number 0.75, and the exhaust is around 1.5, is around 1. Yeah. So, yeah, you can see the difference is higher in this case as compared to this. thing. So this results in the propulsion efficiency for this case is lower, and propulsion efficiency for commercial aircraft is higher because we want a higher speed in this case, whereas the main purpose of this aircrafts are that it wants to have a higher efficiency rather than the higher speed. Now, now the thrust equation. Let us. So this is the answer for the this question, that the propulsion efficiency for fight commercial jet will be higher as compared to the fighter jet. Now, other thing is the area. So the thrust is given by m dot u v exit minus u. U is the aircraft velocity and v exit is the exhaust velocity. So for a now you have a higher thrust. You have a higher thrust for thrust by mu for this equation. Uh, okay, you have higher. Yeah, 1 minute. Is it? Okay, so you have higher thrust by mu for a fighter jet. Therefore, the area is lower for this case. And the efficiency is lower. Thrust by mu is higher, so therefore the area is lower, and also the drag force is lower. Drag force basically represent how much area you have. Higher the area, higher the pressure drag force. Whereas in this case, the thrust by mu is lower. The efficiency propulsion efficiency is higher, and the area is also higher in this case. So yeah, so this is the answer for this question. Let us solve another question. Compare the propulsion efficiency for different types of aircraft.
Sir,
Huh,
sir,
huh.
sir, 1 second, sir. I got. On which basis do you describe the Mach number, sir?
Mach number,
What all the
yeah.
properties? What all the properties will be considering to define the Mach number?
Okay. So what we Mach number is defined as velocity of the aircraft divided by the speed of sound. So this commercial aircrafts. Okay, I'm sorry. Uh, yeah. So these commercial aircrafts, the velocity is nearly around 750 meters per second. Kilometers per second, meters per hour, sorry. Yeah. And the velocity, they cruise at an altitude of 30,000 feet. So your commercial aircraft, they travel at this altitude where the temperature is 216.67 Kelvin. So if you compute the Mach number at this point, so it will come nearly around zero point 0.7 to 0.57 to zero point 0.8. Whereas these aircrafts, they cruise at a higher altitude as compared to this, nearly around 40,000 feet, 40,000 50,000 feet. And yeah, and they cruise at a velocity of nearly about the 1500 kilometers per second, kilometers per hour. Yeah. So this is how you define it. Does it answer your question or?
Yes, sir.
Huh. Okay. Okay. So right. So let us come to another problem similar to this. Compare the propulsion efficiency for different types of aircraft. You have a ramjet, you have a scramjet, you have a turbofan, turbojet, and turboprop. So you have to arrange these um, aircrafts in the decreasing order of their propulsion efficiency. So I'll give you another 2 minutes to answer this. After that, you can answer this question. So. Anybody he wants to answer this? So okay,
Hello.
let us.
Hello.
Huh. Yes, yes, sir. Huh.
Can I answer?
Yeah, yeah. Please, please go ahead.
I think highest propulsion efficiency is for the turbofan,
Turbofan.
and then turboprop,
Okay.
and then come the turbojet,
Okay.
then scramjet. Last one is the ramjet.
Okay. There is okay. The you have okay, but let us see the yeah. It is little scramjet. How? Why do you say scramjet has a higher efficiency than a ramjet, and why a turbofan is having a higher efficiency than a turboprop?
Uh,
Uh,
I think, like we discussed earlier, it depends on the exit velocity and temperature, right? So in the
yes.
turbofan engine, the fan air mass flow mixes with the jet flow,
Hmm.
and so the velocity and temperature comes down.
Velocity and the temperature comes down. Okay. So
Uh, okay, I think in that case also turboprop will be higher than turbofan.
right, right, right.
Yeah, yeah,
So turboprop will be highest, followed by the turbofan, then
okay.
turbojet. Then why do you say this scramjet will be having a higher efficiency than a ramjet?
Um, no, sir, I'm not sure.
Okay,
With a-
okay, okay, okay. No worries. Yeah. So let us see the answer for this. Uh, Basically, let us see the range of the velocity range in which they uh, propel. So turboprop, they propel at a lower Mach number, nearly around zero point 0.5, less than zero point 0.5. Turbofan, they are used in commercial aircrafts where the Mach number is less than 1. Turbojet, they are used in fighter aircrafts where the Mach number is less than 2. And you have another type of engines that are known as ramjet engines. Ramjet are different from a turbojet. I will explain this thing uh, after this. Then followed by the scramjet engines, which travel uh, less than Mach 10. So it is okay. It is less than Mach 10. And rockets, then we have rockets which propel at a higher velocity, more than Mach 10. So higher the velocity, the lesser will be the propulsion efficiency. So this is how we have, this is the correct trend for the uh, propulsion efficiency for all three engines. So yeah, so yeah. Coming on to the thermal efficiency part, uh, yeah. So this, as the propulsion efficiency indicated that the what amount of kinetic energy is being utilized to increase the thrust of the vehicle. The thermal efficiency is the quantification. You if you are in a stationary frame of reference and you have some um, wind that is coming in, which will be equal to the velocity of the aircraft, and the exhaust gases are being expelled by a velocity of uv. So on how much fuel you are spending to increase this kinetic energy is being determined, is being denoted by the thermal efficiency. So the 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 total energy consumption, this can be written as the amount of fuel flow that is being fed into the combustion chamber. This is the combustion chamber. Here, how much amount of energy, how much amount of mass flow rate of the fuel you are giving into the combustor, divided by the QR. QR is the calorific value of the fuel. So this for methane and other hydrocarbons, this is nearly about 50 megajoule per kg. Be it methane, butane, the value is nearly about this. So yeah, so how much chemical energy you are spending um, to which is getting converted into thermal energy and being utilized uh, to increase the kinetic energy of the flow. So this is only for this is defined only for ramjet, turbojet, and turbofan and turbojet engines. Uh, because you have a jet that is helping the uh, uh, aircraft to propel the vehicle. Whereas in case of turboprop, turboshaft, we do not have a we have a thermal efficiency, but it is being denoted by the shaft power. Here the major importance is the shaft power, not the increase in the kinetic energy. So how much shaft power it is being fed after being after burning the some m dot f amount of fuel. Is that clear? Uh, Thermal efficiency part, is it clear for turboprop and turbojet engines?
Yes.
So another thing, last time somebody asked me what is the difference between a turboprop and a turboshaft engine. So this image shows a better version of this difference between the turboshaft and a turbofan. Turbofan, the velocity of the jet after the propeller is is in the direction of the aircraft, whereas in a turboshaft it is perpendicular, and a small amount of exhaust, the small amount of thrust is also utilized to create thrust in these type of engines. Then, yeah, coming on to the propeller efficiency, this is defined mainly for turboprop and turboshaft engine, which is defined as the thrust that is being generated by these propeller blades divided by the energy that is being fed into the shaft. So this is known as the propeller efficiency. This is the shaft power. This is the thrust power, and this is shaft power. This is similar to propulsion efficiency, where we have uh, which is defined for ramjet, turbojet, and scramjet engines. We have something else which is known as equivalent shaft power. This is there is known as equivalent shaft power, where we in this case we have not taken into contribution of the exhaust gases that is being expelled out, whereas equivalent shaft power is the shaft power in the in which is going into the propeller, and this there is some other thrust that is being utilized by the exhaust. So this is the equivalent shaft power. Yeah. So coming on to the another important parameter that is being utilized for uh, characterizing the thrust, the performance of the air breathing engine, that is the TSFC. This is the thrust specific fuel consumption. The unit for this is kg per Newton R. Yeah, so it says that how much amount of fuel is utilized to get a unit amount of thrust for a given amount of time. So this is how the TSFC is defined. So the so if you substitute the thrust power, so you can see that you get m dot a at the denominator, and if you rearrange, you will get the equation in terms of the fuel by air ratio. F is the fuel by air ratio, and the only the velocities, exhaust velocity. Yeah. So this is your TSFC for any air breathing type of engine. Later we'll be using it when we are dealing with detailed thermal cycles for different type of aircrafts. For to have some numbers in mind, a ramjet engine it takes has a highest TSFC, which means that it takes more fuel to generate a unit amount of thrust for a given amount of time. So this takes about 0.17 kgs to generate 1 Newton of thrust for 1 hour. So, whereas your commercial aircrafts takes only very less amount. It's like 30 grams per hour to generate 1 Newton amount of thrust. Whereas the turboprop is even lower, which takes about 0.27 to 0.36, kgs per kilowatt hour. Kilowatt basically is the unit, because here the concern is the thrust. Here we it is the shaft power. So yeah, for a turboprop, we do not define TSFC. Instead, we have something known as brake specific fuel consumption. When we are taking into contribution of the exhaust gases also, then it is known as equivalent brake specific fuel consumption. Okay. So yeah, so these are the parameters which is used in different type of aircraft: turbofan, turbojet, ramjet, and scramjet. This is for turboprop, turboshaft. I think this part is clear. It is very important to note these efficiencies, because in the later stages, when we are doing the cycle analysis of all the aircrafts, these parameters will be utilized extensively. So it is important you have good grasp of these quantities. So is it clear?
Yes, yes.
Okay. So yeah. Coming on to the overall efficiency basically represents is just a product of the propulsion efficiency and the thermal efficiency. So basically, it is the kinetic energy by the energy fed into the combustion chamber, that is m dot f into q r, into the propulsion efficiency, that is the thrust power by kinetic energy change. So you have thrust power by the amount of fuel that has been the amount of energy that the fuel is supplying. Whereas in case of turboprop, you have combustion chamber that drive the shaft, that drive the turbine, that's feeds the energy to the turbine. Then turbine generates the shaft power. The shaft power generates is used for prop, used by the propeller. And so yeah, so the in case of the propulsion efficiency, you have the propeller efficiency, yeah, in this case. So okay. Okay, so coming on to some rocket stuff. So there are two quantities that are used to characterize the uh, uh, rocket rocket performance. One is known as the thrust, and other is known as ISP of the rocket engine. Okay, so this thing you can see, this is ISRO's Mahendragiri Giri thrust stand. It is in the thrust stand is in Mahendragiri, and the rocket that you are seeing here is the engine that will be used in Gaganyaan. So this is how you do the testing for a liquid rocket engine. This is the thrust stand for a liquid rocket engine. At this point, the rocket is station. The rocket. This is the engine, rocket engine. This is stationary, and you have the tanks to supply oxidizer and the fuel. And yeah, you have some open area where the exhaust can go. So this is how you do a static rocket test, rocket thrust measurement. You have something here. You have measurements for thrust. You can measure what is the chamber pressure and other stuff. So here you The other thing you can see here, this is, I guess, uh, NASA's solid rocket booster. Um, this is okay. So let me ask this question first. Why this liquid rocket engines are tested vertically and a solid rocket motor is tested horizontally? Anyone? And this is just an open question. It'll, so the knowledge. So anybody wants to take a guess? Why the solid rocket motors are tested in a horizontal way and why the liquid rocket motors are tested in a vertical manner.
Anything related to liquid distribution, sir? Just a
Liquid
guess.
liquid distribution as in?
Uh, in the atomizer.
Okay, you're saying that the atomizer, so you are injecting the you have a atomizer at this place, so that it goes vertically, is it? Otherwise, it will go like this. This is
Here
what
I'm
you
in
mean?
horizontal. I'm guessing that the distribution in will not be uniform.
Distribution will not be uniform. Okay, so uh, okay, so the answer is not that because uh, the injector that injects the fuel is at a very high velocity at inside this. So, okay, to give you some numbers, the injector velocity, the injection pressure that is there, it is nearly around 100 megapascals, and the chamber is around 60. So you have a 40 megapascals of difference. So at this thing, the velocity is very high. The atomization velocity is very high. So there is no effect of the gravity in these cases. So the distribution is nearly uniform for both the case. But yeah. So okay. So let me answer this. Uh, Okay, so for a liquid stage, it is always advisable to for any two of the rocket, it is always advisable to test the rockets in a vertical way because in a real case also you will be having in a vertical manner. Your rocket will be always vertical. But in case of a solid rocket, if you place in a horizontal way, the thrust stand that will be needed will be very big and huge. So here you can see it is a very small thrust stand. It is there is a block that does not allow the uh, rocket to propel out. Whereas if you place it here, you will be needing a very large amount of mass to hold this rocket engine. Therefore, this is not these are not tested in a vertical way. So yeah. So coming on to this rocket static test, one of the major parameters is the thrust. Another is the ISP. ISP the is the amount of the weight of the propellant that is being expelled out from the nozzle from the rocket engine or any type of aircraft divided by the thrust that it generates. So this is one of the graph which classifies all these air breathing and non-air breathing type of engines. So you can see for a rocket engines the specific impulse, this specific impulse is very less. This is in the orders of this. Okay, you have for a hydrogen oxygen system, you have nearly about 450. Okay, 450 seconds of this. So this is m dot. So you see this. This is the force. This is force per unit time. So the unit will be in seconds. So yeah, so you have 450 seconds of thrust ISP for these type of rockets. For methane engines, methane LOX, liquid oxygen, LOX LS2, you have nearly about 300 seconds. So so it remains something around the on solid rocket motors. It is around 250, 200 to 250. So it ranges about 200 to 400 seconds. Yeah. For a hydrocarbon based engines, you turbojet engines, you have nearly about 4,000 to 2,000. If we switch these technologies to hydrogen based fuels, which is the next future for the next future for the air breathing engines, you can see these values can be extended to other higher um, values. Yeah. So yeah. Okay. So coming on to let us discuss the assignments for this course. Uh, so I hope everyone has submitted done this assignment one. Is it? Uh, has everyone done the assignment one?
Yes, sir.
Yes, sir.
Okay. So let us discuss the first problem. Uh, okay. In a gas turbine, the combustion takes place in which process? Anybody wants to answer this? Anybody? Okay, so the correct answer is the isobaric process, because the combustion here takes place at the combustion chamber uh, is uh, is a constant pressure heat addition process. So yeah, coming on to the question number two, that in a closed cycle based gas turbine, maximum temperature is limited by so yeah, anybody wants to answer? Or okay, so the answer is turbine, because because the maximum temperature is achieved only after the turbine when it the flow enters the turbine. Also, yeah, the combustion chamber after the combustion chamber exit, the turbines are rotating at a higher RPM, which results in the axial load. This is the turbine blading. The axial load and the heat transfer that the highest maximum temperature. The metallurgical limit and the axial load limits this inlet temperature, turbine inlet temperature. So, in modern gas turbines, so nickel-based alloys are used uh, to make this turbine blades. They are also made by another special process that is known as single crystal technology, where you only have that metallurgic. You might have read in your metallurgical class. You have some grain and grain boundaries. So these turbine blades are made by a single grain. So yeah, so this is known as single crystal uh, uh, and directional solidification. So right, and also we right currently there is the research that is going on is what is the efficient way to cool these turbines. So what people usually do is they take the air from the bypass section. This is the bypass section, which is relatively cool. They feed into the feed into the bypass duct, which uh, which goes into the turbine blades and cools it. So this is how the turbine cooling is done. So coming on to the question number three, the multi-stage compressor is desired for which process? So the correct answer is raising pressure of the cycle. Uh, So yeah. So what is? Let me answer. What is a stage? This complete term is little uh, rich in nature. So this what is a stage represents? So a stage here represents a series of a pair of and a rotor, stator and a rotor blade, and you can see as in this case the velocity. This is how the velocity varies along the stator and a rotor. Yeah. So this is what a stage is. It is a combination of stator as well as a rotor. So why do we need a multi-stage? This is something important. Uh, yeah. So basically, what happens if you try to compress, say if you have a 50 bar of delta P, delta P is 50 bar, and if you want to do it in a single stage means only you have a stator and a rotor. This will not be possible because there is something known as the stage loading factor, which depends on the blade geometry and blade geometry. Yeah. So, yeah, this thing represent basically delta H by U square, stage loading factor. So, yeah. So, to have this delta H is the change in the enthalpy across a single stage. So, to have a higher pressurized, you need a higher delta H. For a defined blade geometry, this quantity is fixed. Therefore, if you have to rise a pressure by a large amount, you need a larger U. That is the velocity at higher RPM. You need a higher RPM, which is not desirable for a compressor blade. So what we usually do is we divide the total pressure rise among each stages. This can be divided among all the stages given that U square is fixed. U is fixed. So this is what why it is done. So if you have a some complete delta P of say 50 bar, so you divide this thing into 5 bars. You say 10 bar each. You divide these things among all those stages. So this can so therefore this can be operated at a lower RPM also now. So this is why a multi-stage is needed, and this is how the maximum pressure rise is calculated. Uh, is yeah is attained in the combustion chamber. So this stage loading factor will be dealing in the later part of the course, where when you will be dealing with the turbo machinery aspect of the aircraft engine. Yeah. So coming on to the exhaust, solution four, the addition of exhaust gas heat exchanger to a simple, adding exhaust has gas heat exchanger to a simple gas turbine improves the work output, reduces the work output, improves efficiency, reduces work output. So the correct answer is yeah. So the correct answer is improves efficiency. As you can see, the exhaust gas temperature is higher than the turbine, the compressor exit temperature. This is the compressor part. So there is a chance, there is a availability that we can use this temperature difference to increase the temperature after the compressor. And after this, 5 to 3, you can use your fuel to increase the uh, temperature, where you will be uh, uh, you'll be saving this small amount of fuel that is being utilized. So yeah, so the correct answer is it improves the efficiency. So Coming on to the question number five, that was the advantage of using a twin shaft arrangement for a turbine is to. So, so twin shaft, basically, I'll explain you what it is. The the annular shaft that is there, it is having the shaft that connects the turbine and the compressor is in annular in nature. Annular in nature. The this is known as high pressure turbine. This is known as high pressure compressor. This is low pressure turbine, low pressure compressor, and this is low pressure turbine. So these things are coupled together, and this process is known as spooling. Spooling. So basically, this is required so that they can have attain variable speeds. I think there was a problem in this question, that the answer mentioned was this, is it? Is it like so? This is the correct answer, to have a variable speed, because in a same rotor you cannot have different speeds. Okay. Coming on to the question number six, which is which of the following engine is suitable for low altitude and low speed flights? So this I have discussed in the previous lecture. So this is the turbo piston prop engine, which uh, which cruises at a lower velocity and a low altitude. So coming on to question number seven, how does the propulsion efficiency for a turboprop varies with the flight speed? So yeah, as discussed in the last lecture, for a turboprop engine, it increases to a certain height and then decreases. So the correct answer is the C, which is first increases and then decreases. Okay. So coming on to question number eight. The propulsion efficiency for a aircraft is defined as okay. So today we have discussed these things. So that is the overall efficiency. The okay, total thrust by input thrust. This is the dimensions are inconsistent, so it does not represent the efficiency. So yeah, uh, this is the thrust power by total input energy. It is the overall efficiency. Then this is thrust power to the change in kinetic energy is the propulsion efficiency. Then the change in the kinetic energy to the input fuel is the thermal efficiency. So the correct answer is C, thrust power to the change in kinetic energy. Okay. Coming on to question number nine. The working fluid through a gas turbine remains in. So, okay, what does a phase means here? Phase basically means with phase is the state. Basically, whether it is in single state, is in as in gas, liquid. I'm sorry, these are the state. So, for the for a two phase, it means you have a mixture of either gas plus liquid, you have liquid plus solid, you can have gas plus solid. So in a gas turbines, we have a single phase only, that is a gas. However, in Rankine cycle, we can have two phase flow, but it is not desirable, because two phase flow can these liquid particles, they travel at a very high velocity, and when they impact the turbine blades, they can result in erosion. So as you can see in these two images represents the turbine blade that is being eroded by the two phase flow. So this is why this is the two-phase flow is not desirable in turbines. Rather, we only stick to single phase, that is the gas or vapor state. So okay, the correct answer is it remains in a single state, single phase. Coming on to the question number 10, that choose the incorrect statement from the following for a turboprop engine. So, okay, so let us read all these question statements. Majority of the thrust is provided by the propeller. This is true because in a turboprop you have a small exhaust, and the major portion of the thrust is through the propeller. This is true. Turboprop are designed to fly at a supersonic speed. This is false. Triple spool is common in these engines. Yes, it is true because you have a gearbox, you have a compressor, you have a turbine. Turbine and compressors are twin spooled, and one spooling is done for the propeller. This is true. It is used for low altitude application. This is true. So the correct answer is B. They they are designed for supersonic. The reason being is if you try also to run this turboprop at supersonic speeds, what will happen? The blade they will be cruising at a supersonic speed, and there will be shock wave that will be formed, and this will create in a higher loss. So as you can see in this image, this is the compressor blade. This is the compressor blade, and when it is traveling at a uh, uh, Mach number greater than one, so you can see this flow discontinuity, which is known as shock, is observed in this flow. What happens to this? What Why these are not desirable? The answer to this is that these results in stagnation pressure loss, and this is not at all desirable for any type of engines. So, okay. Coming on to question number 11, the overall efficiency for a gas turbine uh, is lower uh, than the reciprocating engine, as the maximum temperature attained in a gas turbine is lower. Is it? Overall efficiency for a gas turbine is lower, as the maximum temperature is lower than the reciprocating engine. The correct answer is lower. So, yeah. So, because in a reciprocating engine, the temperature you can achieve is more than 2200, whereas in a gas turbine, the temperature is limited to 1800 Kelvin. So correct answer is this. I guess I have made it long. Yeah, it is lower. So okay, okay. Uh, so let us end this lecture by some thoughtful question. That is, I think probably people have read about this afterburner. You might be knowing about this. Anybody? What afterburner is?
Yes, we spray fuel on the uncombusted gases after the turbine.
Okay. So what does it do?
Then it will increase the thrust momentarily.
Right, right. Yeah. So for a fighter aircrafts, so if you want to increase the thrust, what we usually do is we take the energy from the turbine to run the compressor. The rest energy, the bypass air that is there, we mix. Okay, this will be, yeah, this is okay. This is the afterburner for. This is a typical design for an afterburner. This is the air coming from a bypass duct, and this is the hot stream that is coming out of the turbine. So after that, there is a some section where these fuel mixes, these two streams mixes, the and we inject this fuel so that the cold stream further can be the fuel can ignite and increase the temperature, and then um, you have the nozzle, variable area nozzle, where you can control the area ratio. You can compress this thing, you can uh, change the area of the nozzle, and you can control the thrust. So this is how the afterburner works. So yeah, okay. So this ends the lecture. So if you have any questions regarding this topic or any other doubt, I'm open to it.
Hello, sir.
Yes.
Sir, I couldn't attend the previous lecture. Is there any way that I can get that knowledge?
Yeah, okay. So I have recorded that lecture and it is in my YouTube channel. So I'll share you the link. Or what you can do is you can note my email ID, you can mail me, I'll send it through that. So if I'll message my email ID in the chat box, there you can submit your questions also. I'll answer them. I'll try to answer them.
Okay, sir.
Yeah. So yeah. Any other doubt?
I heard out, sir.
Okay, okay. So,
Why?
huh,
Hello.
huh.
Yeah. Why reciprocating engine efficiency is higher than a gas turbine engine? And one
Uh,
more question
hmm,
is, you told about we can go for a higher temperature in reciprocating engine.
yes.
So what is the reason? Because in gas turbine also we are using uh, high temperature resistant material.
Hmm.
So
Okay.
why we?
So consider this. If you have gasoline-based engine, so the combustion occurs there at a constant volume. So the constant volume process. Okay. So if you ignite a fuel at a constant volume as compared to constant pressure, the temperature attained is very high because the amount of work there is the internal energy is not doing the work to expand the flow, right? For a constant volume.
Okay,
So there the temperature you can attain is very high as compared to this constant pressure process.
okay. And
Uh,
just one clarification. So
yes.
constant volume combustion means in reciprocating engine
Hmm.
at the compressed volume is that
Hmm.
combustion is happening?
Yeah, so if you see the cycle, the diagram for the Otto cycle, so you have the compression process followed by a constant volume heat addition. Is that correct?
Okay, sir. Does that means before the piston moves backward, the full combustion takes place?
Yes, yes. You utilize all the energy that is being fed into uh, the gases. Yes.
Okay, okay, sir. Thank you.
Yeah.
Thank you.
Huh. Any other doubt? Okay. Anyways, I'll uh, write my email ID to this chat box. If you have any doubts, you can please mail me. I'll be available to answer all your questions. Yeah. So if you don't have any question, you can leave the meeting.
Okay, thank you, sir.
Okay. Thank you.
Thank you, sir.
Okay. Okay. Thank you.